Hey guys, we're going to look at implicit differentiation here. So implicit differentiation, this is when we cannot isolate the y all by itself. Our derivatives that we have done before have typically just been of a function that's already had y isolated. So we technically are always doing chain rule. So if I do the derivative of 2x right here. So we know that the derivative of y in terms of x right here is 2, but that is times the derivative of that x, which is really 1 right there. And we have been able to do the derivative of y in terms of x because everything right here is in terms of x. We don't normally say that we're doing chain rule when it just has an x there because times 1 doesn't change anything. But here, when I look at this first function, I cannot easily isolate y. So we have to move into something called implicit differentiation. And anytime you have to take the derivative of y, you need to take it in terms of x, just like we always have, because we're trying to find the derivative of y in terms of x. So that makes it necessary for us to have a chain rule, and we have to show that we are taking the derivative of all our y's in terms of x. And let me show you how this works. So this first term is in terms of x. So that's an easy derivative to do. It's just for x. We know that. Plus this next one. This is a product rule right here. We have two functions multiplied together. So we take the derivative of the first. That's x's. So that's just 2x. Leave the second one alone. Plus, leave the first one alone times the derivative of the second. And this is where we have problems. I know that the derivative of y to the third is 3y squared, but this is the derivative in terms of y. I need the derivative of y in terms of x. So that is that chain rule that I was talking about. We still need to know what y was in terms of x. So anytime you have that wrong letter, you need to have this chain rule of dy dx in there. Next one in terms of x, that's just a 1. Next one, not in terms of x. So 2y times dy dx, the derivative of y in terms of x, whatever that is, plus 3, we know the derivative of a constant is just 0. So now this is closer to what they want us to find. They want us to isolate that dy dx. They want us to find the derivative in terms of x. So I'm going to leave x squared times 3y, so I'm going to call it 3x squared y squared dy dx over here on this side. I'm going to move the 2y dy dx over by subtracting. And then I'm going to move everything that doesn't have a dy dx over to the right-hand side. So the 1 is there. I'm going to do minus the 4x and then minus the 2xy cubed. So now I've got my dy dx on one side. I just need to isolate it. So since these both have dy dx, I can factor it out. So I have dy dx factored out times the leftovers, which would be 3x squared y squared minus 2y equals this side over here. We're just going to copy it down. We haven't done anything to it. And now find dy dx. Well, we just need to divide this stuff away. So the derivative of y in terms of x of that implicit function up there that we could not isolate y is this right here. All over. We're going to divide by that stuff that we don't want. And it's that right there. Now, usually they'll say find the tangent, which is like what this next one is going to do, and you'd end up putting x's and y's in here. So here we go. Consider the equation of the circle, x squared plus y squared equals 1. Find the tangent lines at the point 1/2 and then root 3 over 2. So I'm going to do A right here. We're going to first find the tangent, right, or the derivative, because we know that for a tangent line we need a slope. So the first one's in terms of x. So 2x, which is perfectly fine, plus the derivative of y squared, that's the wrong letter, so 2y dy dx equals derivative of 1 is 0. Isolate your dy dx so you can have your slope, so 2y times dy dx equals negative 2x, and divide everything away from dy dx. So our slope, our derivative, same thing, is negative x over y. Now, they want this at the point 1/2 root 3 over 2. So substitute x where x goes and y where y goes. So at that point, we would have negative 1/2 over root 3 over 2, which simplifies to be negative 1 over root 3. You could rationalize if you want to, but you don't have to. So this is our m. We have a point, we have a slope. let's write it in point slope form because they didn't ask a certain form. So y minus y1, which is root 3 over 2, equals our new slope, 1 over, or negative 1 over root 3 times x minus x1. And I'm going to leave it in point slope because they didn't tell me which way to go with it. Next one, at the points of the circle with x equals 0. So they didn't give me a full ordered pair, so I need to know where is x equal to 0. What are the points they're wanting me to find this at? So go to your original function, 0 squared plus y squared equals 1. Well, we know that's y squared equals 1. And now the y values that would go with this would be plus or minus the square root of 1, so just 1. So we have two tangents, actually, that are happening here. We've got one that happens at 1, 0, and we have, or 0, 1, sorry, I said it the opposite way, and then one at 0, negative 1. So we have two tangents that we're working with. We already know the slope from up above, dy dx, is equal to negative x over y. We already did the hard part up there, so we're just going to borrow it from part A. Now, at each of these points, at 0, 1, that would have a slope of negative 0 over 1, which is just 0. At 0 over, or 0, negative 1, same thing's going to end up happening, a slope of 0. So a slope of 0 are lines that happen like this. These are our horizontal lines. So the way that we write those equations are just based on the y value. So we have a tangent at y equals 1, and we have a tangent at y equals negative 1. So that was not too terrible. Example number 3. I want you to pause, and I want you to see if you can do that implicit differentiation for this. Just pause and try it. Okay, so once you isolated dy dx, you could have gotten one of these two, depending on how you felt about all those negatives or not. It doesn't really matter. We're going to end up in the same tangent line in either way you go. It doesn't matter. So it's really just preference there. So that's your derivative. Now, my point for this, I only know the x value right now. So we're going to have to substitute 0 for x. So I would have 0 squared plus y plus 0 times cosine y, that would just be 0, equals pi. So my y value is at pi. So my point that we're working with is 0 pi, right there. So here's my point. This is my slope. Write the equation of the tangent and the normal. Remember, normal means perpendicular. So we've got two that we're going to work with. So the derivative, the dy dx, at the point 0 pi, if we substitute those things in, we're going to have 0 for x, okay, so that's gone, plus cosine of pi, so cosine of pi for the y, and then 0 times anything is 0, so that's gone, over negative 1. So cosine of pi is 1. Oh, actually, negative 1, sorry. So we have negative 1 over negative 1, which is a positive 1 right there. So there's your slope for your tangent. So tangent, they didn't tell me what form to go in, so I'm going to go point slope. So y minus pi equals 1 times x minus 0. You can leave it there, or you can simplify. If you really want to, you can go y equals x plus pi with all the simplification. It's not really that difficult to simplify. My normal line is perpendicular to the tangent, so instead of having a slope of 1, we have a slope of negative 1, still the same point that they want you to go through. So now we just got to change it up. Y minus pi equals negative 1 times x minus 0. Again, you can go into y equals mx plus b if you really want to. Not that big of a deal to get there. But they didn't ask for it, so we don't have to. Okay, so we'll save the rest for class. If you really want to try example 4 and 5, go for it.